Welcome to Comparative Anatomy of Vertebrates. Today, we are going to explore the structure of a typical vertebra, which is the fundamental building block of the spine in all vertebrate animals. We will uncover how this incredible bone perfectly balances immense weight-bearing strength with delicate, precise flexibility to keep animals moving. To begin, imagine a tall tower made of stacked wooden blocks with a highly sensitive, vital electrical cable running right down the middle of it. If the blocks shift too much, the cable snaps. If they are glued completely solid, the tower cannot bend in the wind without breaking. The bones in your back, called vertebrae, are exactly like these ingenious wooden blocks. They stack to keep you upright, interlock to let you move, and form a thick, bony armor to keep your spinal cord perfectly safe. Now that we understand the basic idea, let us look at the formal anatomy. A typical vertebra is the fundamental repeating structural unit of the vertebral column in all vertebrate animals. It is composed primarily of a massive, weight-bearing central body known as the centrum. Sitting right on top of this centrum is a bony ring called the neural arch. This arch creates a hollow protective tunnel known as the vertebral foramen, which allows the delicate spinal cord to pass through safely from the brain to the rest of the body. Building on the centrum and neural arch, we find various bony levers projecting outward from the structure. These are called processes, or apophyses. They serve as crucial attachment points for the many muscles and ligaments in the back. Together, these distinct components create a highly dynamic structure. They perfectly balance the immense load-bearing capacity of the solid centrum with the precise, controlled articulation provided by the processes and the muscles attached to them, allowing for complex movements. Before we move on, let us see this with a concrete visual example. Here is a cross-section of a typical vertebra. At the bottom, you can see the large, round centrum, which bears the body's weight. Above it is the neural arch, enclosing the empty vertebral foramen where the spinal cord lives. Notice the projections: the neural spine at the top, the transverse processes on the sides, and the zygapophyses. These are the mechanical levers where muscles attach to move your back. Having seen its structure, we must ask why this specific design is so important. The vertebra solves a major biological engineering problem: how an animal can be strong and flexible at the exact same time. Without this modular design, vertebrates would either be immobile, rigid tubes or soft organisms, unable to support their own weight against gravity. The specific shape of these bones dictates exactly how an animal moves, allowing the spine to adapt to different ecological niches, like a cheetah running or a human walking. This brilliant modular design leads us to the biomechanics of how the centrum handles weight. We can model the compressive stress on the centrum using a standard mechanical formula. Sigma equals F divided by A. Here, sigma represents the compressive stress, measured in pascals. F stands for the downward compressive force, or weight, measured in newtons. A is the cross-sectional surface area of the centrum, in square meters. If the downward force increases, stress increases significantly. But if the area increases, the stress decreases, keeping the bone safe from fracturing. Now that we have our formula, let us apply it to a human standing upright in a relaxed posture. We are given a downward force of 500 newtons on the fourth lumbar vertebra, which has a cross-sectional area of 0.001 square meters. We want to find the compressive stress. We use our formula, sigma equals F over A, and substitute our values. Dividing 500 by 0.001 gives us a final answer of 500,000 pascals. Physically, this means the bone easily supports the load, well within its safety limits. Moving from biomechanics to taxonomy, biologists frequently use a specific mathematical notation to summarize the entire vertebral column of an animal. This is called the vertebral formula. In this notation, each capital letter represents a specific anatomical region of the spine, such as cervical for the neck or thoracic for the chest. The subscript number attached to each letter tells us the exact count of individual vertebrae found in that specific region, giving us a quick snapshot of the animal's skeletal structure. This notation naturally leads us to a simple equation for calculating the total number of vertebrae in an animal. N total equals C plus T plus L plus S plus CA. Here, N total is the grand total of vertebrae in the entire spine. The variables on the right represent the subscript numbers extracted directly from the formula for the cervical, thoracic, lumbar, sacral, and caudal regions. By simply extracting these numbers and adding these distinct regional counts together, we get a complete picture of the spine's overall length and complexity. Let us see this formula in action with a healthy domestic dog. We're given the vertebral formula C7, T13, L7, S3, C20. We need to determine the total number of vertebrae in the spine. First, we extract the subscript numbers for each anatomical region. Then, we set up our addition. 7 plus 13 plus 7 plus 3 plus 20. Adding these together gives us a final answer of exactly 50 total vertebrae. This tells us the dog has a fairly long and complex spine. Now that we have calculated the total, let us interpret what these numbers mean biologically. The 20 caudal vertebrae tell us the dog has a highly flexible and elongated tail, which is crucial for balance. The consistent count of 7 cervical vertebrae is a fascinating evolutionary hallmark shared by almost all mammals, from tiny mice to towering giraffes. Meanwhile, the 13 thoracic vertebrae indicate the exact number of rib pairs the dog possesses to protect its vital organs like the heart and lungs. We have covered a lot of ground today, so let us review the key takeaways. A typical vertebra is a masterpiece of evolutionary engineering that perfectly balances protection, support, and movement. The massive centrum acts as the primary weight-bearing pillar, managing compressive stress. The neural arch forms an impenetrable safe house for the delicate spinal cord. Finally, the projecting processes act as mechanical levers, allowing muscles to pull and twist the spine with incredible precision. Great job following along. You now understand the foundation of vertebrate anatomy.